In this video, we will learn how HSPICE computes DC operating points, how to interpret the results, and how to perform DC sweep analysis. The command that will be shown here follows Synopsys simulation and analysis user guide. Well, let's begin with the concept. What does DC analysis mean? DC analysis ignores capacitors and inductors because when we are doing this kind of analysis, capacitors will be treated as open circuits and inductors will be treated as short circuits. So with this kind of analysis, what we are trying to find is the node voltages and the branch current. And this is basically the starting point of all the analysis. So it's very important to keep in mind that if the DC operating point is wrong, then everything else in the circuit will be wrong. Let's open a new notepad. And we can write DC let's build just a basic voltage divider. So we will have in our net list V1 in 0 DC, 10 R1 in and out, 5K R2 out 0 and 5K as well, and then gonna have an end. Let me explain what we have. In this part we have R1 and R2 that are two equal resistors, and we have V out that equals 5 volts. I mean, this is V in, but V out will equal 5 volts. And just like I said before, this auto P simply computes the bias point. Let's save this and run to check the results through the files. Then let's upload it to HSPICE, DC op. Let's then start running our simulation. Everything seems to be working fine. And then HSPICE DC op SP SP. Okay. Let's see, and then let's update here. And we have these files generated. Let's open the one with Lee's extension. So with this file, we can check the result of our analysis. Here we found the node voltages and the currents going through V1, as you can see here. The node voltage on these two sides, and there is also the total voltage source power dissipation, this one, and we have the current. And you are seeing the current with a negative value because of the sign convention and also because of the current direction reference. Let's now try to do something a little bit different, using multiple voltage sources. Then V2 out 0 DC, something like 2 R1 out 2 can just save this, or let's rather open this file and make the change. Since we changed the main file, we'll have to rerun this. Alright, and then if we double click on this file, we're gonna see the results. So here it is, and the voltage on the nodes will now be different because we made these changes. One of the things that is important to keep in mind is that HSPICE will be doing most of the stuff for us, like KCL and KVL. All of that will be done under the hood. Now, let's talk about the DC sweep analysis. What does it do well? The DC sweep analysis lets us see how a circuit responds when a DC source changes. And let's write a netlist for this particular example. We can simply copy and paste this one. Let's just do this. Then we have, let's do some changes here. R1 in, out, okay. Zero, also 1K. In order to do that, we have to use this command line .dc v1 0 like 10 and 0.1, and let me explain this line. What do we have here? Well, basically what we have here is this .dc, just like you can see, but after that we have this, we have something like a source, and this source has its start, has its stop, and it has its step. That's what we see here. We have the source name, we have its start 0, its stop 10, and we have its step 0.1. And whenever you want to do the sweep analysis, the name source should match exactly the one you have in your circuit. Let me write this separately so that it doesn't become confusing. Alright, and there we have it. Let's save it as DC op sweep speed. So if we upload this and we run the simulation, let's see what we get. Let me just reuse this, just change a bit. Oh, okay, there seems to be an error, and it says that there is an attempt to redefine R1. Let me check the netlist. So yeah, because this is the problem. So I wrote R1 twice. This is supposed to be R2. Let me save this. And let me try running this again. Alright, now everything seems to be working fine. After that, let's do this and this. Okay, let's check the lease extension file. And basically, what is happening here is that we defined this to do the DC sweep, but we didn't tell HSPICE what quantities to measure. Therefore, it is omitting the results. So what we'll have to do is to tell it what quantities it has to measure. Let's change here a little bit. Let's write like this. And then here, this is the part where we define our voltage divider. In this part, we are defining our DC sweep. But after we define a DC sweep, we also have to tell HSPICE what quantities it has to save. So let's do this. And here we are supposed to have a probe DC here and V out. So with this, it should work now. Let's save it and see. Let's just close this firstly. So let's go back and double click on the lease extension file. Or before doing that, let's set something else to our netlist first. Let's set at the bottom this line 2. And this line will be very helpful to read the results and to keep them for further analysis. So let's save it. And then let's rerun everything again. We have this. So this is what we're gonna get with the lease extension file. But this is not very helpful when it comes to truly understand what is going on. So we need to plot this in order to have a better sense of what's going on. And for that, we're gonna use wave view. Let's see. So there seems to be a problem with our wave view, and to solve that, we're gonna have to add something else to our netlist. So we come here, we can get rid of this, and then let's just have option post 2. It should solve the problem. And then, alright, Let's now open the wave view. This is the one that we need. Alright, so let's plot V in and let's plot V out. And let me explain what's going on here. So just like we defined in our netlist, here we have a relationship, a linear relationship between the output and the input. And it is important to notice that the one that we are sweeping is V in, which is represented by V1 in our netlist. And this is the one that we are sweeping. So this one is supposed to go from 0 to 10. And let's try using the cursor here. So if we use the cursor, let's just, alright, at least until it's fine. Let's use the cursor and notice that its maximum will be 10 because we are doing this swipe from 0 to 10. But for V out, when it comes to V out, we will notice that because of the voltage divider, it will have half of the input value. Since we are having 10 in the input, its half will be 5. Let me zoom out again. If we are having 10 in the input, its half is supposed to be 5. And we can confirm this looking at this value. Here we have the input and here we have the output, which by the voltage divider is supposed to be half the input. Here we have V in, and here we have V out, which following the formula, where V out would equal V in times R2 over R2 plus R1. And that will be basically V in over 2, which is half of the input. That's why we are seeing V in having 10 and V out having 5. Or we can even plot these two together in this manner. Alright then, let's try now to write a netlist where we're gonna perform a nonlinear sweep. We just do small changes. Let's change here. Supposed to be 0 now. And let's remove this. Let's have this and this one. And also this. Then yeah, the DC sweep here will be the same. Just remove some space. This one's also okay. Let's have one here. Yeah, everything seems to be fine now. 2. Let's upload this. And now let's rerun the netlist again and get its output files. Alright. Yeah, seems to be okay now. And then let's open wave view. Oh, not this one, but the other file. Alright, let's see what we have here and here. And this is what we get. Know that in the previous DC sweep example, the circuit contained only resistors, so the plots were straight lines. But in this circuit, we replaced one resistor with the diode, which is a nonlinear device. That's why you can also see that in the plot, the behavior now is nonlinear. Look at this point, and you will notice that at the low input voltage, the diode is essentially off, and that's why you will see that basically there is no voltage drop across it. That's why we see this flat region in this part. But as the values are being and as Vn increases, we also notice that there is a sort of exponential behavior now in this plot. And with this, we can confirm that the circuit is behaving according to what we expected now that we replaced one of the resistors with the diode, which is a nonlinear device. So this is just to show how this sweep analysis is especially useful for visualizing this kind of nonlinear behavior. Let's then close this. And I believe that we are done. Now that we understand these operating points and this is sweep, in the next video we will move into transient analysis and time domain behavior. See you then. Thank you for watching.